Hey there! Today we are going to be talking about neutrinos. We'll see what they are and their properties. Neutrinos are subatomic particles, meaning they're one of the building blocks of matter, just like the electrons, for example. They're represented by the Greek symbol nu, which basically looks like the letter V. Neutrinos are fundamental particles. Fundamental because you cannot break down a neutrino into simpler particles, or it's not made by the combination of other smaller particles. Neutrinos were first given the name neutrons by the scientist Wolfgang Pauli, but later they were renamed neutrinos by the scientists Edoardo Amaldi and Enrico Fermi. This was because the name neutron was already given to another particle. Neutrino is an Italian word for the little neutral one. Little because neutrinos have a tiny mass, and neutral because they carry zero electrical charge or they're electrically neutral. These particles are grouped under the group of particles called fermions in the subgroup leptons. Let me briefly explain what this is. Elementary particles are basically classified into two, that is into fermions and bosons. For now, you just have to know that fermions are further divided into quarks and leptons. The quark group contains 6 types of quarks, while the lepton group contains the electron, the muon, the tau, and the neutrinos. Anyway, neutrinos are grouped under fermions in the subgroup leptons. Neutrinos, as far as we know, come in 3 types of flavors: the electron neutrino, the tau neutrino, and the muon neutrino. They're represented by the Greek symbol mu with the subscripts E, mu, and T to distinguish them from one another. A neutrino can change from one type to another. For example, the sun produces only electron-flavored neutrinos. Coming from the sun to Earth, 2/3 of these electron neutrinos can turn into muon neutrinos or tau neutrinos. The term physicists use to describe this property of neutrinos where they change from one type or flavor to another is called oscillation. So we say neutrinos oscillate from one flavor to another. The scientist who proposed the idea that neutrinos come in different flavors was Bruno Pontecorvo. Then, along with his Russian colleague Vladimir Grubov, he proposed that neutrinos can oscillate from one type or flavor to another. The oscillation property of neutrinos came as a surprise to other scientists. They did not want to accept it. This is because the Standard Model, which is like the periodic table of fundamental particles describing elementary particles, had already deemed neutrinos massless. For neutrinos to oscillate from one type to another, they have to have mass. The Standard Model had proved itself trustworthy when it came to other particles, as predictions were right. So scientists did not want to accept the idea that the Standard Model could ever be wrong. But later, there were experiments which proved that neutrinos do oscillate from one type to another, which indirectly means they do have mass. I know, I started this video by telling you that neutrinos are subatomic particles. I'm not gonna say they're not subatomic particles. What I want you to focus on is the word subatomic particle. What comes to your mind? A particle which is found inside an atom, right? Although neutrinos are subatomic particles, they do not remain trapped inside an atom. They just like to travel. The trillions and trillions of neutrinos that passed through your body when you started watching this video are now somewhere else traveling to who knows where at the speed close to the speed of light. Unlike the other subatomic particles, we do not find neutrinos trapped inside an atom. Just like most elementary particles, a neutrino has an antiparticle counterpart called antineutrino, represented by the nu sign with a bar over its head. Let's sidetrack and talk about particles and antiparticles. Most elementary particles have corresponding antiparticle counterparts, which in most cases are similar to them by mass, but opposite to them by at least one property, such as electrical charge, for example. Let's see another elementary particle, for example, the electron. The antiparticle counterpart of an electron or an anti-electron is called a positron. It's identical to the electron in its mass, but it has opposite electrical charge from the electron. The electron is negatively charged, while the positron or the anti-electron is positively charged. We represent the electron with the letter E and a negative side over its head, while a positron is represented by the letter E and a positive sign over its head. So this is all to say that a particle's antiparticle counterpart is identical to it in its rest mass, but opposite to it in properties like electrical charge. So do neutrinos and antineutrinos oppose each other by their electrical charges? No. Remember, the neutrinos are electrically neutral particles, so how do neutrinos and antineutrinos oppose each other? Electrical charge is not the only property by which a particle and its corresponding antiparticle could oppose each other. There are other properties, like the lepton number, for example. Earlier, we said neutrinos are grouped under leptons together with the electron, the tau, and the muon. Each lepton is assigned a lepton number of +1, and their antiparticle counterparts are assigned a lepton number of -1. That is, while the electron, the muon, the tau, and the neutrinos are assigned the lepton number of +1, their antiparticle counterparts, that is, the anti-electron or the positron, the anti-muon, the anti-tau, and the anti-neutrinos have a lepton number of -1. So let's go back to neutrinos. How do antineutrinos oppose neutrinos? Neutrinos are electrically neutral particles, so it cannot be by electrical charge. So, neutrinos and antineutrinos oppose each other through their lepton numbers. Neutrinos have a lepton number of +1 and antineutrinos have a lepton number of -1. Neutrinos are fascinating particles. They're one of the most abundant particles in the universe. They're produced during nuclear reactions inside the core of stars like the Sun, or from nuclear power plants on Earth during supernovae, that is when stars die and explode, when energetic particles from space collide in the upper atmosphere of the Earth during radioactive decays, including atomic bombs, and so on. Although they're extremely abundant, it's extremely hard to pin them down or track them down. This elusive property comes from the fact that neutrinos don't like to interact with matter. Neutrinos can travel a light year's worth of lead without interacting with any atom. They can pass through the Earth like a bullet cutting through a fog. What are you doing right now? Watching this video with your computer or smartphone? Are you alone? Well, if you think you're alone, you're not. You have trillions of subatomic particles as your subatomic companions. Nice, isn't it? Trillions of neutrinos are passing through your body right now and they don't leave a trace. Every single second, 100 trillion neutrinos pass through your body. Imagine how many neutrinos pass through your body your entire lifetime. In 1 second, 100 trillion neutrinos pass through your body. An hour has 3,600 seconds, so in an hour, 360 quadrillion neutrinos pass through your body. A day has 24 hours, so in a day, 8 quintillion 640 quadrillion neutrinos pass through your body. A year has 365 days, so in 365 days, 3 sextillion 153 quintillion 600 quadrillion neutrinos pass through your body. If, say, you live for 80 years, 252 sextillion 288 quintillion neutrinos pass through your body. This is only considering the neutrinos which come from the Sun. Don't forget the other sources of neutrinos we mentioned. And it's without considering the 9 months you've spent inside your mom's belly. But why can't you feel any of these neutrinos? This is because of what we said earlier. Neutrinos are shy to interact with any atom inside your body. During your entire lifetime, from all the neutrinos which pass through your body, maybe one could interact with an atom inside your body. So neutrinos are shy introverted particles which detest mingling. Because they can effortlessly pass through anything and don't like interacting with matter, neutrinos are called ghostly particles. So if neutrinos don't really like to interact with matter and start to track them down, then how can we detect them? Or how did scientists come to know about them? We'll look at their history and the ways we can detect them in other videos. Thank you for watching and see you next time.